Well, in the preceding videos, we've learned that we have a lot of tools at our disposal to solve for axial force, shear, and bending moment diagrams and beams. But I think as you're already figuring out, if we have any hope to enjoy some of the finer things in life, we're going to need to come up with a much faster way to solve for these diagrams. Now, I think we could come up with that better way. I like to call it the method of inspection. By further leveraging our relationships between forces and shear and between the shear and bending moment. Alright, you know what that means. It's time now to take a look at your top secret mission number 2. Or just flip to the next page in your notes. We're going to see that, hopefully you'll see that the method of inspection will really make your life easier for a lot of load cases.
Alright, so let's go ahead and see if we can somehow use the relationship between shear and load and between moment and shear to make things a little bit faster. Now, again, we said v of x was equal to minus the integral of omega x dx and over some range, right? Well, what's the integral over of any function? If we go back to calculus, right, that's just the area under that function. The area under the omega x curve. Let's not forget the negative sign there. So that basically means the change in shear is equal to negative of the area under the omega x curve. And likewise, for moment, the change in moment is going to be the area under the v of x curve. And there's no negative sign this time. And then don't forget, these areas are on a particular range, right? So this tells us the delta V or the delta M over a particular range. And then this will help us plot things much faster. Now, in order to plot them, we're going to, of course, have to follow a few rules. We don't get away from those rules, so we have kind of a procedure listed here that we can follow. And so there we go. If we take a look at our procedure, we look at first compute reactions, then 2 we start going down. We begin by plotting the shear diagram, use the area under the load curve to determine the changes in shear. No loads cause no change in the shear diagram. Concentrated loads cause instantaneous jumps in the direction of the force. Distributed loads cause a linear change in the shear diagram. Linear loads cause quadratic changes, and so forth. Jumping down to moment diagrams, we see that we use the area under the shear curve to determine changes in the moment. If we have v equals 0, then there's no change in the diagram. Concentrated moments cause clockwise on the structure, cause positive jumps. And then we see that relationship, constant v, linear change in shear, linear v, quadratic change. So again, remember they're related by the integral. So let's go ahead and plot the shear moment diagrams for example 4, but we're going to use this information and do it much more quickly. So I'm going to go ahead and sketch in my reactions. AX, of course, is 0 here since there's no horizontal forces. And AY and BY, I think we can pretty quickly tell from symmetry that AY equals BY, and they both have to be 9 kilonewtons acting upwards. All right, so if I follow the rules from the previous page, I'm going to start with my shear diagram. So working my way kind of from left to right on my shear diagram, I start at A. A is at the end of the beam. It starts kind of at 0, but then we have that point load, AY, that pushes it up a value of 9 kilonewtons. Now we have no load acting between A and the middle of the beam, so the shear remains constant at all points until we get to the middle, at which point we have an 18 kilonewton force down. That pushes our diagram down. If we were at positive 9 and we go down 18, we end up at negative 9 kilonewtons. Again, nothing changes from here to the end. At the end, we have 9 kilonewtons pushing us back up to 0. It's always good to see that our shear diagram closes back to 0. I'll go ahead and put my positive and negative sign conventions in there for shear. All right, now it's on to the moment. Now we said from the previous page that the change in moment over some particular range was going to equal the change in area under the v of x curve over that same range. So in order to plot the m of x, I'm going to need some areas off of my shear diagram. And so I'm going to have to go back to my shear diagram and calculate a few areas. So let's look at it piece by piece. If I go from x equals 0 to x equals 5 meters, the change in moment will then be the change equal to this area in green, or I'll call this A1. A1, the total area is base times height, or 9 kilonewtons times 5 meters, for a total change of 45 kilonewton meters. So delta M from x equals 0 to x equals 5 is positive 45 kilonewton meters. So what that looks like is we start at 0 because we're at the end of the beam and we're at a pin at A. And then at the middle, we have 0 plus 45 gives us positive 45. Now I have to use the relationship between shear and moment. I know that shear is constant. Moment is the integral of a constant. The integral of a constant is a linear function. That is a linear function. I tried my best to make it a straight line. And so we say we would have to know that relationship to draw the linear line there. I'm going to repeat this on the range of 5 to 10 meters. So from x equals 5 to 10. That change is going to be equal to the change shown in blue, or A2. I'll calculate A2. I'll calculate it as negative 9 kilonewtons times 5 meters. I know you can't really have negative areas, but and mathematically in calculus, we can kind of get negative values. It just means it's lower than the x-axis. But it does mean that delta M changes by negative 45 kilonewton meters. If I start at positive 45 and I get to the end, 45 minus 45 gives me 0. Again, constant shear gives me a linear moment diagram. I go ahead and I add my bending element, and I now have my shear and moment diagram complete for this instance, for this beam. I hope you found that a lot easier, especially as we're going to do a lot of these. Let's try it again on example 5. Example 5 is a very common case. A lot of times in buildings we'll have distributed loads on beams. Even in bridges we have a lot of distributed loads on beams. So this is one that we have to be very comfortable with. All right, again, I need to come up with the resultant force. The resultant force is the base times height of the load, so that's 6 kips per feet times 16 feet, or for a total of 96 kips. That acts in the middle of the beam, or 0.8 feet from both A and B. If my total resultant force is 96 kips, then AY and BY are both 48 kips by symmetry. If you needed to sum moments about point A to solve for BY, you're welcome to do that. You'll get that BY has to be 48 kips, and then some force in the Y would show AY is 48 kips as well. All right, so let's plot V. We start at 0. We jump up a value of 48. Let me make that line kind of more clear. So we start at 0. AY causes a shift up to 48. Now I need to look at the change. Remember, the change in shear from point A to B is going to equal negative times the area under the omega x curve. And so I need that area under the omega x curve. I'll call that A1. I already calculated it. It's 6 kips per feet times 16 feet, or a total of 96 kips. Now remember, the change in shear from over that range is negative times that area. And so that's going to give me negative 96. So at the beginning, at point A, I'm at 48 kips. 48 kips minus 96 kips is negative 48 kips. And I get to the end. Now I see a BY. BY is going to push me back 48 kips back up to 0. Because my distributed load is constant, a constant 6 kips per feet, when I take the integral of distributed load, I get an integral of a constant will give me a linear line, so I see that relationship follow. Let me sketch this a little bit better so that the negative 48 is kind of symmetric, and we'll see better that the middle passes, the shear is 0 exactly at the middle there. All right, lastly, we'll calculate our moment diagram. At the end of the beam and at a pin, our moment at point A has to be 0. The moment at B has to be 0 as well. We'll need the areas again, so just go through A2. The area is the area for a triangle, 1/2 the base times height, 1/2 times 48 kips times 8 feet. Doing some math there. I calculate that to be 192 kip feet. Likewise, we're going to need the area for the remaining portion of the shear diagram, the area shaded here in blue. I take the area shaded in blue, it's just negative times the area in orange. So plug in my numbers, I get that the blue area is a negative 192 kip feet. Now remember, this is my change in my moment. My moment originally starts at 0. It changes from 0 by a positive value of 192 at the middle. And then from 192, I add A3, the blue area. 192 minus 192 gives me 0 again at point B. I want to recall that m of x is the integral of the shear. The shear is linear, so the moment diagram has to be quadratic. And so I need to put in a parabola. Now, my quadratic function can either be concave up or concave down, so I have to make a decision right now as to which it is. So I also knew that the relationship was that the derivative of moment equals shear. So at the very middle of my beam, the derivative of the moment has to equal the shear. The shear value at the very middle is 0. And so that means dm dx has to be 0 right at the middle. Dm dx is the slope. So I need a line, a slope of 0. And so that means that the parabola that I left here is the one that's correct because it has a slope of 0 at the middle. All right, we follow it all the way around to the other side and we get something like this. We finish it off. We can also think of the slopes at either end. The slope at 0 has to be positive 48, so you can see this parabola has a positive 48 slope, or something that looks closer to that compared to the previous one. Another way I like to look at this is if I look at a change, that change I shaded in deep orange, that change is a certain area and it goes up. This blue area, like if I move another foot, this blue area is a little bit less. I move another foot, this green area is a little bit less. And so as I get closer to the middle, I have less and less of a change on my moment diagram. So that's kind of how I think of it when you're trying to make the decision. I would say when in doubt, though, most of the time our moment diagrams tend to be concave down. So if you're going to make a wild guess, that's probably what you should do. All right, I hope you enjoyed the fast way method of inspection.
Congratulations! I think you guys are ready to tackle axial force, shear, and moment diagrams in the real world. Now, I think we better get out of here before someone catches us.